Today we study various forces shaping our world, and the first of these is the gravitational force, which is nothing but a type of pull that acts between two masses. In context of this lesson, one of those masses is often the earth and the other is some object. It could be a brick, ball, or a hammer. But the important thing to remember is that the direction of this force is very specific and always directed towards the center of the earth, or simply in the minus y direction, straight towards the ground. So when an object is in free fall, if we ignore the air resistance, the only force acting on it is the gravitational force. And we can relate this force to the acceleration due to gravity g using Newton's second law, that is, force on an object due to gravity is equal to the product of its mass and gravity g, that is 9.8 meters per second square. Now, something you must remember is that this force of gravity doesn't disappear when the object is at rest. It still very much exists. It is just that it is cancelled by an equal and opposite force exerted by the table back onto it. The second force, very familiar to us, is the weight of a body, which we can say is the gravitational force that the earth exerts on it. So you might say that how is it any different from the force of gravity that we just discussed? Well, you would be quite right in making this observation, and it would be true in most instances, but not always true. So imagine you are standing on the moon. The acceleration due to gravity there is different from that of earth. So the formula mass into gravity of moon would result in a smaller force than mass into gravity of earth, or your weight would be less on the moon compared to earth. But let's get back to earth and let us say you are in an elevator that's speeding up or slowing down. In that case, your weight can actually change and we call it the apparent weight. So your real acceleration, which otherwise is assumed to be g, is influenced by the elevator's acceleration, and it can increase or decrease depending on whether the elevator is accelerating up or down. So when you multiply this real acceleration with your mass, you might feel lighter or heavier. So again, you end up having an apparent weight different from your real weight that we assume to be simply mg. And we learn more about our weight in elevators in a separate lesson. Now, the term mass and weight are often used interchangeably, particularly in everyday conversation. So mass of a body is a fixed quantity. Higher the mass, higher the force needed to accelerate it. And that is exactly what Newton's second law illustrates. So if you are given a large rock and a small rock and you apply the same force F on both, from experience you can tell that you will be able to accelerate the small rock more than the large rock. In fact, you can see this mathematically as well. If F is fixed, this value of A would be more than this one simply because the denominator here is smaller. Weight, however, is a force exerted on a body by the pull of the earth. Objects having large mass also have large weight. And if you've tried to lift a small rock and also a big rock, it is obvious that it is more difficult to lift the large rock with a lot of mass off the ground because of its large weight compared to the small rock. So the magnitude W of a body's weight is directly proportional to its mass m. Also, since weight of a body is a force, therefore a vector quantity. So feel free to write it as a vector equation where required, while mass is a scalar quantity. So the next force we will study is called the normal force, and it is a force exerted by the surface that supports an object, and it always acts perpendicular to the surface. So when you're standing on the ground, while you might believe that you are pushing the ground in downward direction, which is true, the ground is also pushing you up and that is what we call the normal force. And why do we call it a normal force? Well, definitely not because the other forces are abnormal. It is because it comes from the mathematical term normal, meaning perpendicular, and you can see that here the force due to the floor on you is perpendicular to the floor. So if we have a box sitting on a table, it is pressing down on the table due to the force of gravity. And let us say this force is Fg. And for a moment, assume that there is nothing like normal force. Then just looking at this figure, you should be able to say that the logical thing to happen is for the box to keep moving down under the influence of force Fg, and this box should just break through the table and sink into the earth, simply because there is no other force acting on it. But of course, we know that this does not happen because of the equal and opposite normal force that the table also exerts on the box. And therefore, if you were to draw a free body diagram of the block, you would see that the forces acting on the block are these two. So if we were to write the Newton's second law of motion equation for this situation, how we would go about is that first, on the left hand side, we'll put all the forces. So we have Fn taken as positive because it is acting in the upward direction, minus Fg, and minus because the force is in the downward direction. And so this becomes the net force, which equals mass into acceleration that this net force creates. And we know that Fg is equal to mg. So if you put mg in this equation, what we get is Fn minus mg is equal to ma. Then Fn is equal to mg plus ma, or Fn, or the normal force, is equal to m into g plus a. Now, word of caution here is that we've already factored in the sign of g in this equation, but a, which is a final acceleration as a result of combination of forces, that is the net force, can be positive or negative. However, for this particular situation, we can see the box is going nowhere. That is, it is stationary. So its acceleration is 0, or Fn is equal to mg. That is, a normal reaction equals mass into gravity. Another thing you must remember is that when using this equation, you must first work on one side of the equation and then on the other side. Or in simple terms, first establish the net force on the left hand side and then say to yourself that this net force will create an acceleration on the object, which is this, and appears on the right hand side. Or if you know the value of acceleration, you could first establish the right hand side and then say that this acceleration is due to a net force that is on the left hand side, and then go about establishing the left hand side. Moving on, let's study a force that you encounter every single day but have not thought much about, and that is the force of friction. So from our experience, we can say that when we slide an object over a surface, we feel a resistance to motion in some measure, and this is mainly on account of bonding between the body and the surface. So this resistance is what we call the frictional force. An important thing to remember is that this force is directed along the surface, parallel to it, but always opposite the direction of the motion. So if you're pushing the book to the right, the frictional force is working against you, pulling to the left. So now we come to the force of tension, which will show up quite often in physics problems. So picture a rope attached to a body and you pulling the rope so that the rope becomes taut or straight. What happens is that the rope pulls on the body with a force directed away from the body and along the rope. And this force is what we call a tension force, because the rope is basically in a state of tension, which means that it is being pulled straight. And we say that the tension in the rope is the magnitude T of the force on the body. So if the force on the body from the rope has magnitude T of 50 newtons, the tension in the cord is 50 newtons. Also, a rope or a cord is often considered massless when compared to the mass being pulled, and it is also assumed to be unstretchable. And you would apply this condition or these two assumptions in most numerical problems you will encounter. So you can say that a cord connects two bodies and it pulls on both bodies with the same force T. And one thing you must always remember is that tension is always a pulling force. After all, you've always seen a rope pulling an object and never experienced a rope pushing an object. So hopefully this lesson has reduced a bit of the gravitational pull of confusion, and if you wish to glide through physics problems, do check out our specialized playlist. It's packed with valuable tricks and insights. And if you found value in today's lesson, a thumbs up would be fantastic. Until next lesson, stay forceful.